Imagine feeding like 100 random coin flips into a computer and then mathematically proving that they control the stock market. Today, we are taking a deep dive to uncover how least squares estimation actually separates the real signal from the noise.
Right. Our mission here is really to explore how researchers use these mathematical tools to interpret, messy real-world data relationships. Because you don't want to get fooled by your own calculations.
Exactly. And we all know the basic concept of linear regression, right? You have a scatter plot of data and you snap a trend line right through the middle. Conceptually, you can picture taut rubber bands connecting every single data point to that line,
Oh yeah, I love that analogy. And least squares estimation mathematically finds the exact position where the total stretch of all those rubber bands is at its absolute minimum.
which works beautifully for a simple two-dimensional scenario. Like, one of our source papers predicts roadway salt concentration based purely on the area of the road.
Yeah, for a single variable, it's incredibly elegant. But, you know, reality is rarely two-dimensional.
Right, which scales us up to multiple linear regression, because now you're dealing with a matrix of variables. Our semiconductor manufacturing source highlights this perfectly. Predicting wire bond pull strength requires factoring in both wire length and die height simultaneously.
To handle that mathematically, researchers use normal equations. That is essentially the matrix algebra that allows us to solve for multiple predictors at the exact same time.
So it ensures that the total squared error across every single dimension is minimized. But if we scale that up, there's a massive trap here.
Oh, definitely.
Because standard R squared measures the proportion of variation explained by your model, right?
Ah,
Since it measures any variation caught by the math, throwing 100 random variables into the matrix will just artificially inflate the score.
yeah, the model accidentally captures tiny, completely meaningless fluctuations in the noise and just counts it as a successful fit.
That sounds like a disaster for real research.
It is. And that is why researchers rely on adjusted R squared. It explicitly factors in the number of regressors and the sample size.
So it mathematically penalizes the score when you add variables that don't genuinely improve predictive power.
But wait, doesn't adjusting the score essentially mean we are just arbitrarily punishing the model for being complex? I mean, sometimes the real world actually requires 100 variables.
Well, it's a calibration for degrees of freedom, not an arbitrary punishment. You only take a hit to the score if the new variable's contribution doesn't actually outweigh the statistical cost of adding it.
Ah, I see. So it prevents the model from just memorizing the noise instead of learning the true signal.
Exactly. But even with a heavily scrutinized adjusted R squared, the sources emphasize a mandatory reality check, which is analyzing the residuals.
Right, the leftovers. It's like looking at a dartboard after a game. If your aim is true, you misses. The residuals you should be scattered completely randomly all around the bullseye.
Yeah. If you plot those residuals and see a random, patternless scatter, your errors are perfectly uncorrelated. You're in good shape. But what if they aren't random? Like, what if all your misses are pulling down and to the left?
Then your model has a fundamental bias. The specific patterns mentioned in the sources are huge visual red flags.
Right, like if those residual darts form a funnel shape where the errors progressively widen, or even a double bow shape.
Yeah, that means we are dealing with heteroscedasticity. The core assumption of constant variance is completely broken.
Because if the variance of your errors changes depending on where you are in the data set, that perfectly taught regression line just isn't reliable across the board.
Exactly. The model is, well, it's effectively blind in certain ranges.
So least squares estimation gives researchers the mathematical rigor to optimize outputs, but the heavy lifting really happens in the error checking. You have to interrogate those residual dots to prove the trend isn't just an illusion.
It absolutely forces you to look beneath the trend line and question the underlying variance.
Which leaves you with this thought. Since reliable predictive models depend entirely on perfectly random constant errors, how many of the algorithms secretly governing your daily life are actually hiding a chaotic funnel of unpredictable errors, just waiting for those rubber bands to snap?